Hi, thanks for joining us today for building real-time inference pipelines with Ray Serve. My name is Adam Brindell. I'm a technical trainer with Anyscale, and we're going to be working with the Ray platform today and focusing on ML inference. So just to give you a preview of where we're going to be going before we kind of build everything up, we're going to be building a ML multilingual chatbot. And to kind of make things a little more interesting, we're going to use a chatbot that only knows English, but we're going to support a user that's speaking English or French. And that's going to kind of give us an opportunity to build a little bit more of a complex application. So instead of just having a chatbot, we're going to have multiple models. We're going to have some additional services that represent Python business logic in one case and statistical models in another, to kind of give you a feel for how you could build a real application using RayServe and assembling the different components. So this diagram may look a little complicated. It'll make more sense by the end, but this is where we're going to get to by the end of today. Now, before we get into the code, let's talk a little bit about what Ray is for folks that haven't seen it before. So fundamentally, Ray is a platform for high-performance distributed scale-out applications focusing on machine learning. And to give a quick kind of bottom to top view of kind of the stack here, at the very bottom, we've got compute resources of some kind. So it says cluster. This could be a cloud. This could be on-prem. It could be Kubernetes. It could be physical machines, VMs, but some kind of compute resources. Above that, we have Ray Core. So Ray Core contains primitives for these high-performance distributed applications, and you may never actually need to use the APIs in Ray Core. So everything is built on Ray Core, and you certainly can use it to build interesting custom applications. But as we move up this stack, we'll see that the real benefits with Ray are these higher level layers that give us simpler, more basic abstractions for doing common tasks. So above Ray Core is Ray Air, which we're going to zoom into in just a second. And at the very top, integrations and ecosystems. So you probably recognize most of the logos in there. And the idea is that Ray comes out of the box with first-class integrations for most of the popular tools in machine learning ecosystems. So Hugging Face, which we're going to be using today, and you probably recognize XGBoost, PyTorch, PyTorch Lightning, Gradio, Weights and Biases, and a whole bunch more. And the idea is that you don't have to build those integrations. Those integrations are kind of baked in into the APIs that will just link together so we can easily build applications. So we're going to zoom now into the sort of teal colored box that says Ray Air. And Ray Air focuses on high level, easy to use abstractions that solve the integration and distributed compute problems for common ML workflow tasks. So starting with things like data ingestion. So this could be coming from static storage, things like Delta Lake or Parquet. It could be coming from other systems, so things like Apache Spark or Dask. Then we have training. So we can use various frameworks to either train models from scratch. Also, one of the popular things people are talking about now is fine-tuning models. So we can take a model checkpoint and we can go and fine-tune it for our use case. And that falls under Ray Train. Then we have hyperparam tuning. So that falls under Ray Tune, where we have a set of APIs that integrate with common libraries and popular algorithms like Optuna, HyperOpt, and even combinations of those so we can tune our models. And then the area we're going to be focusing on today, over on the right, which is RayServe. So RayServe is, we'll talk about that a little bit more in just a second, but it is a microservices framework focusing on serving machine learning applications, so online inference, but it also supports all the other stuff that we might need to build a serving application. There's one other piece to Ray Air, which is the RL-lib for reinforcement learning. That doesn't figure into exactly what we're doing today, so it's not on this slide. But you might want to take a look at that if you're looking at doing reinforcement learning. So zooming in even tighter onto the section that we're going to be focusing on today. So building and deploying online inference application using RayServe. And what this diagram is illustrating is that we have a lot of flexibility with RayServe. So we can have lots of nodes. We could have one node. We could have lots of nodes. And we're going to look at a package of functionality or a chunk of logic that we're going to call a deployment. And we'll get to the code for that in a minute. And the idea is that we could have one or lots of different deployments representing different parts of functionality. And we could have lots of different deployments on a single node, or we can have deployments spread across lots of nodes. So there's the reason why there's not a lot of specific detail in this diagram is because it's so flexible. So we can have deployments in kind of any combination that makes sense. And then further, we can support additional volume by implementing multiple replicas of our deployments. And in fact, Ray can auto scale the replicas in various ways to handle our loads. So we might have a deployment that represents one piece of functionality, and maybe under load, it requires lots of replicas, maybe on one machine, maybe on lots of machines. We might have some other deployment that actually doesn't really require a lot of replicas, and that can scale independently with its own resources. Again, we don't have to worry about which machines it's going to end up on, whether that's one or a lot. So I know that sounds like a lot of things going on, but the really cool thing is it's pretty much automatic. So we don't need to design an architecture that worries about which things go where or exactly how many replicas we're going to have. So this diagram kind of captures the flexibility that we can define some basic units of functionality and let Ray take over from there. If you want to follow along either right now or after the presentation or come back to this and take a look at it later, there is a GitHub repo up here where it says under this shortcut URL. So I'm just popping this open so you can see we have a public repo here with both a regular and a GPU-backed version of the notebook that we're going to look at today. And I've also got links here to the Ray documentation and the Ray Summit, which is our conference later on this year. So definitely consider coming to that and learn all about the latest and greatest pieces of Ray and meet all of the Ray folks. And what I'm going to do now is jump over into some code. So let's go and take a look at building a multilingual chat with Ray Serve. Now, this notebook can run in Google Colab, so you don't need to have any other infrastructure if you want to run it. I'm running this on any scale, so I'm not going to run some Colab-specific cells because I've got different hardware behind this. But if you want to run it, we're going to be using GPU, and we're going to be illustrating some really advanced features like fractional resource allocation, and that actually does work even on Google Colab. So you can dive in and try all of that stuff. So I'm going to skip down here to the third cell. I'm going to run some imports, and then I'm going to connect my notebook kernel to my Ray cluster, which I already have up and running. And if you're running in Colab, you'll have a slightly different version of this line that will start up a new cluster. And the first thing I want to do is illustrate this idea of a deployment with a really basic chatbot service. So this is built on a Hugging Face Transformers chatbot model. I'm not going to get into the details of working with Hugging Face because you've probably already seen that, or you can learn from their great materials how that works. I'm going to focus on the Ray integration side. So we'll get our import here. And you can see the main thing that makes this into something that works with Ray specifically is this decorator at the top that says serve.deployment. And the serve.deployment is going to tell Ray that this is a deployment. So this is a chunk of functionality that represents a particular service. And I've actually added another parameter here that says num GPUs 0.5. So we don't need to do this. If we don't care about being frugal with our GPUs, we don't need to worry about it. But the really cool thing is that we can let Ray manage fractional resource allocation and optimize placement and management of replicas of our service to use our resources as efficiently as possible. And I actually set this up because on Google Colab, you may know you only have one GPU. So if I have 3 services, and I will have 3 today that use GPU, if I just want each one to reserve all of the GPU memory, that's not going to work. But what I can do is I can tell Ray, hey, this service needs half of a GPU. The other 2, the translator services we're going to build, use just a quarter of a GPU. That adds up to 1. So I can actually get this to work on Colab. When you run it yourself, you'll see it actually does work. In a more industrial situation, you probably wouldn't be limited to 1 GPU, but because GPUs are expensive, especially at scale, you're going to be interested in optimizing your services to use just the resources they need. And you want your scheduler and your autoscaler to be able to arrange these services in a way that makes sense. So this is a kind of a really cool feature that we're using already right here. The class itself, we've got a constructor that grabs hold of some state. So this is where we would, create any kind of state we want, load up a model from a model store. In this case, we're creating it with some Hugging Face APIs. Then we have 2 other methods here. The most important one is this one, get response. This takes the user input and the history of the chat conversation and sends it through the chatbot and gets a response. The async def call here is kind of a helper wrapper for accessing this via HTTP. Because what we're going to see is that with these deployments, we can talk to them via REST over HTTP, or we can talk to them directly through Python invocations, or different combinations of those. So that's what we've got set up here. So I'm going to evaluate that code. Just to give you a little bit of a view into some of the other things we can do with deployment scaling that we're not illustrating necessarily today, I've got a little chunk of code here highlighted that shows an auto-scaling config param that we can give to the serve.deployment, where we can say things like, I want a minimum, maximum number of replicas. I want to start with a certain number. I can even talk about the relationship between load and how many replicas I want. So there's a lot of control I get there. Let's go and take one more step towards launching this. I'm going to go chat.bind here. That creates something called a bound deployment, which is the last step before we can launch this, which we're going to do in this next cell where we do a serve.run. So this is actually going to start an application. It's going to expose this deployment, and we're going to get back a thing called a serve handle that we can use to talk to this. And we'll get this running here and make sure that it's working. So it looks like it's started up. Let's go and talk to it. We've got, once again, this icon that kind of represents notionally what we mean by a deployment, this package of functionality, so we can decompose our application into all the relevant services that we want. We've got one chunk here. We're going to add other ones, and we can have multiple replicas of those. So I'm going to send a message. This is a conversation from the Hugging Face docs. If you're wondering why I care so much about my friends eating carbs, I'm just using their example because I want to make sure that I'm getting the same responses. So here I've got a response from the chatbot, and it looks like that's working. And notice the way I send this message, I'm actually doing this just through Python here. So I'm taking the serve handle, I'm calling my getResponse method, then I'm doing .remote, which is a Ray API that says to Ray, I'm accessing an object, or I'm running a task that may be somewhere else in the cluster. And then I'm going to get the string back from the response there. I'll build up my history. So history is just a list of strings that the chatbot uses for context. And I can send another message. So say, I'm not sure. And I get another message back from the chatbot. And if you're playing along, you can have some fun with this and send some more messages to the chatbot. The last thing I want to do before we build something a little more complicated is show that this does work with HTTP. So here's another message. We're going to build a JSON document that encapsulates the message that we're sending along with the history. We're going to fire that JSON document up against the endpoint. So by default, we're on port 8000 here. And we'll decode the JSON that comes back, and we get another response. So this is just to show that we can talk to these services in various ways, depending on what's most convenient. Now we can run different applications potentially at the same time on our Ray cluster here, but for now I'm going to delete this and undeploy the various deployments that I just, replicas of the deployment that I just created. And we're going to build something a little bit more interesting next. So if we're working in a more production environment, and taking on challenges that are bigger than just wrapping a Hugging Face model, we're going to want to be able to handle some more requirements. So what do we get from Ray that makes it so helpful for this? So probably the biggest thing is the developer and integration operation experience. So there's a single platform, right? One platform, a small single set of APIs that we can use for pre-processing, training, fine-tuning, batch prediction, which we're not seeing today, online inference, reinforcement learning, and it's all just one small set of APIs. So there's zero integration there. As we zoom down into kind of more functional and non-functional features here, we have things like fine-grained resource allocations. We talked about that a little bit with the GPU. So we can actually scale at the level of functions and classes. And that can be done automatically. You can imagine you probably don't want to manage scaling every single function, but that can be done, and it can be done automatically. And we can do that in addition to, or instead of, scaling at the level of things like containers with Kubernetes. So we may have Kubernetes and that level of scaling, but we can also do this more fine-grained scaling. Automatic batching, because you may have models where the model throughput is much higher if we can batch our data, but the API for the service is one request in, one request out. So automatic batching. And then Ray gives us a lot of infrastructure features to minimize unnecessary data movement, unnecessary serialization and deserialization, data locality aware scheduling, and other good stuff. So to illustrate like a little bit more complicated application, we're going to build a chatbot that can speak English and French. We're actually going to do it two different ways. So first, we'll do it kind of a basic way with a bunch of services where we procedurally use Python to orchestrate those. And then we're going to visit one of the newest Ray APIs called the Deployment Graph API and see how, as an alternative, we can create a static graph that describes the flow of our data, still in Python. So we don't need any other meta language or anything. We're still using Python, but we can create a static declarative graph and still have dynamic behavior in the model. So we're going to look at both of those. The basic recipe here is we're going to build a translation service for French to English and English to French. We're going to build a language detection service so we know what language the end user wants to use. And then we're going to build a routing or dispatch service for this first implementation that looks at the language the user is using and decides where to send the data. So that's kind of the recipe. We're going to be doing most of this stuff with Hugging Face. So for our translation service, the logic is a basic transformers pipeline from Hugging Face. One of the cool things we're going to do here is we're actually going to use two different models. So one model translates English to French, but it doesn't know how to go the other direction. That's the T5 small. We're also going to use a Helsinki NLP model that can translate from French to English. And we're going to do this because we want to illustrate how we can create a single class that represents an interface, a chunk of functionality, but we can instantiate different flavors of that within our application. So in this case, we don't need to duplicate code or build some custom version of a service for English to French and vice versa. What we're going to do is create slightly different versions of the bound deployment. So we'll take this deployment and we'll do, in one case, a .bind with English to French translation task and the key for a particular model. And in the other translate.bind, we'll give it the French to English task and the other model. So this gives us two different bound deployments that we can use in the appropriate places. Next thing we're going to do is build a language detector. So this is an example of how not everything has to be deep learning. This is a traditional natural language processing n-gram statistical approach. It's tuned for very small or short documents, which is what we would expect to have in a chatbot. So that's why we're using this library. And it's just some simple logic that delegates to this LinguaPy library, and it outputs either EN for English or FR for French. So that's our language detector. And then we're going to bring it all together here in our endpoint service. So this endpoint is what we're going to actually expose. This is going to take the calls and do all of the routing and dispatching and return the result. Now, the most interesting piece in here so this is a similar structure to what we saw before. The most interesting piece is probably under get response. So we're using async pattern here. So first of all, because in a large deployment sort of setup like this, we don't want anything to block unnecessarily. So we want everything to be asynchronous as much as possible. In a few cases, we may need to block in order to get some value that we need to control flow. So there's probably the most interesting piece here is a situation like this first line where we get an object reference from calling await. And then we go and await on that object reference. That might look a little bit unusual at first, but the idea is that if we don't need to block here at all, we wouldn't need the second await. Everything would be async. In this case, I actually need the Python string object lang in order to decide whether to translate. So there's an extra await there. And that's similar to the extra awaits down below. That's probably the most interesting thing here. And at this point, I can actually launch this application. Give this a second to get running here because we've got this serve.run. And we can start talking to it, and let's see if it understands English. All right, so we're looking at the first part of the response. We're concatenating a couple of pieces together in the response here because we need some history information. And that gets particularly interesting when the end user is speaking French. So here we have the end user speaking French, but we actually have to capture an English version of the input and an English version of the output in order to build the history. Because remember, the chatbot only understands English. So when we give it the history context, that all needs to be English. So all of that is just working here. We haven't really gotten under the hood into how this works. That's kind of beyond the scope of where we can get to today, but I've got some links to the docs that we can look at if you're interested. So now we have a slightly complicated application, and we've done it in one particular way. But I want to introduce an alternative way to solve this problem. And so I'm going to delete this application, kind of undeploy the pieces that we've just deployed. And I want to talk for the rest of our session here today about the deployment graph API. So this is one of the newer APIs in Ray. And what it does is it gives us an option to separate the flow of calls and the flow of data from the logic that's inside of our services. So at first you might wonder, well, why would we want to do that? Like, doesn't this make more complexity? Well, certainly you're going to want to decide whether that makes sense for you, but there are reasons why you might want to separate this. So it might be valuable to add a layer of indirection or abstraction so that we can more easily create and compose reusable services. Right? We can kind of create more modular, granular services that represent specific pieces of functionality, and then have kind of a separate set of tasks potentially that arrange those. The DAG API is actually used in other places in the Ray platform as well. So you kind of get some more functionality for free. So if you've seen, for example, the Ray workflow API that uses some of the same pieces. So if we invest in learning and using this DAG API, we can get functionality kind of for free across the platform. And even though we're composing, say, one DAG or directed acyclic graph that represents our application, just to be clear, we're not kind of bundling that up into one chunk that is kind of an opaque box that needs to be scaled. We still keep all of the granular resource allocation, locality-aware scheduling, auto-scaling, all of those things at the more granular level. So we're not giving any of that up just by composing our application flow into a DAG. So, okay, to get started with this deployment graph API, I want to start with something really simple and build up a little bit from there. So at first, we're going to pretend that the end user is only ever speaking French. So we don't need to detect language. We always need to translate, and the flow is going to look something like this picture. The French input will go through a translation service to English. We'll get a chat response. We'll translate that back to French, and the user will get that back. Now, if you're following really closely, you might realize, well, the history doesn't fit in there. So how would we continue the conversation? We'll come back to that. So the first version, kind of the hello world here, is very straightforward and linear. And we're going to start out by creating an input node. So this is a special kind of node defined by Ray that represents the data that's coming into our service. Now, even though there's one input node, we could still have multiple values coming in. So you can see here, I decompose this input node using a context manager into the user input and the history. And then I'm going to build up this graph by grabbing the deployment and the method that I want to use. And I'm going to call .bind on a particular node. And that's going to kind of link one node up to another one in this graph. So this is going to produce a node called user input English. And then I'm going to feed that along with the history into chat get response .bind. That will give me a chat response node and so on. Eventually, I have an output I want to use, and I give that to dagdriver.bind, where dagdriver is a Ray API. See up here. And that handle that comes out of that is going to become the application that we launch. So this will wire up our whole graph. So behind the scenes, all of the relevant replicas are being deployed and wired up. And now I should be able to talk to it in French and get some kind of response. And okay, so we're getting a response there. So that's working. But this is too simple. So I'm going to throw this away. And I'm going to take one more step of additional complexity before we build the full-on application. So if we wanted to continue this chat, the one additional piece we would need is the history. So we would need kind of an English version of the data. We would need history. coming out. So how do we get more than one thing out of our service? Well, we can put nodes into our graph that manipulate, assemble data in different ways. And it's very lightweight to do that. So a common pattern, we're not doing it today, but an example where you see this all the time is machine learning ensembling. So in this diagram, imagine deployment 1 is one ML model, deployment up through N are other models. And then I've got some deployment that represents my ensembling logic. So maybe it's a voting mechanism or an averaging, or maximum, some other mechanism. But the idea is I can consume multiple scores, make some decision, and produce some output. In our case, we're not doing anything quite that complicated. We're just joining some strings. And in fact, I can make a deployment that's even lighter weight than the ones we've seen so far. This is just a single Python function, but I put the @serve.deployment there, and now it's a deployment. It takes in 3 values, and you can see it concatenates them with a little pipe delimiter, so we get one single output. And I've called this thing combine, and I'm going to use that in just a sec. I'm going to create some new bound deployments. Every time we build a new application or a new DAG with the deployment graph API, we want to create new nodes. And that's because although we have some nodes that we created before, we don't want a new DAG to have nodes that really belong in another graph, right? That could get a little bit messy. So every time we create a new one of these, we'll create new nodes. These are lightweight because the nodes don't actually contain the logic. That will happen later. These are just the descriptions of what's happening. So I've got some nodes here, and then I'm going to wire everything up with the same pattern we saw before. The new piece here is this line that I've highlighted. So we're going to do a combine.bind, so another bound deployment. We're going to feed in the data from the user input English version, the chat response English version, the chat response French version, and we'll get one output, which we then launch. We'll call this thing enhanced linear over here. And the names are just so that we can find these applications by name later if we want to delete them or adjust things. And this will take a few seconds to deploy, and let's just go and make sure this works. What do we expect to see here? Well, a French response, but also the pieces we need for history. So notice what we've got out here is the French response, but also these strings, which are the English equivalents that we need for history. So now we've seen a little bit more of an interesting flow. And that brings us to kind of the last piece we want to build, which is the full-on conditional flow. This is where the user can speak English or French. We have the translation services and everything else. Now, this gets kind of interesting because it may not have been obvious so far, but the graphs that we're building are static graphs. The graph doesn't change at runtime. Now, in our multilingual chat, our control does change at runtime, right? We either invoke a translation or we don't. So how's that going to work, right? There's a little bit of something to think about there. And the pattern that we're going to use is to wire up everything in a static graph and then to have some deployments potentially behave differently depending on the data they see at runtime. So it's not going to change what calls where, but different data may flow depending on what's happening at runtime. So in this case, we're going to be routing data into potentially additional places, and some of these services will decide dynamically what to do. So to be a little more concrete about that, the specific thing we're going to change here is our translate service. So this deployment is now going to get a little if-else block, and the translate is always going to be called, and it's always going to receive the user language. But if the user language is English, then the translate will just become a no-op, right? We won't translate from French to English because it's already English, and we won't translate back from English to French later because we want English anyway. So we can adjust the behavior of this service based on the data flowing through, and that's like a 2-line change. We create our deployments and bind them the same way, and now we have a static graph where everything flows in a uniform way. But we get the conditional logic behavior that we want. And we're going to wire up this specific graph so that the user input goes to a couple of places. It goes to the language detector over here. It also goes into the translator. So the translator always sees the user input. From the user input, we're going to get a English version, either because it was originally English or because we've translated it. But this node is always going to represent English. We're going to feed that into the chat service because it only ever works with English. And we're going to also feed the response from the chatbot into the English-French translator. This flow is always going to happen, but if the user wants English, this translator won't really do anything, right? So we have a single flow, a single graph, but with dynamic behavior. And then we just join everything together with our same combine node, and we attach our output, do our DAG driver.bind, launch it, and we should have, in a second or two, we should have a multilingual chatbot using our graph deployment API. Let's test it out. So if we talk to it in French, we get back a response in French, but with history elements in English, which we know is important. And we can talk to it in English, and we get what we expect there too. So it looks like everything is behaving the way we want. So this is lots of fun because it gives us flexibility. Also notice that we didn't have to write the deployments differently depending on whether we were doing imperative dispatch using Python, which is a perfectly fine way to work, or whether we were using deployment graph. So it's not that we need to do things in a radically different way. We can pick the style that makes sense. It's all Python, and it all works together. So to summarize what we've been looking at here today, RayServe is this microservices framework for serving ML. It's the model serving component of a larger Ray platform. And these key features include high performance, large scale operation with heterogeneous resources, right? So you've got your ARM machines, you've got your different kinds of GPUs and other accelerators, FPGAs. We can work with all of those at the same time. Fine-grained resource allocation, like our fractional GPU work, auto scaling, simple interaction with other parts of the platform, out-of-the-box integration with Hugging Face and lots of other libraries, but we saw Hugging Face today, and different ways of composing and orchestrating services using different styles. I've got some more links here. Definitely take a look at the Ray docs, join the Ray community on Slack, join the meetup, open an issue. If you break something, please let us know. And maybe you want to fix something or even just fix a typo in the docs. Feel free to contribute, open a PR, and I've got a couple more links to share right here. And just to remind you, we've got the repo where you can get a hold of the GPU or the non-GPU version of this notebook, the Ray docs, and the Ray Summit in September of this year. Hopefully we'll get to see you there.